Hello and welcome to today's webinar presentation, How Using Phoenix Can Halve the Time Spent on Preclinical PK Analysis. My name is Christopher Mehl and I am the Customer Support Manager for Farsight Corporation. I've been with the company since 2003. So this is a webinar and you will have plenty of opportunity to ask questions. The best way that you can do this is via the chat window in the WebEx. Simply click the question mark icon on the floating toolbar, and this will open a Q&A window on your system only. And then just simply choose the default selection, all panelists, type your question and click send. And we will do a Q&A session at the end of the web presentation. I'd like to begin with a acknowledgement of Gilead Sciences. So during a recent users group meeting, Rachel Lansdowne from Gilead Pharmaceuticals Incorporated presented a case study. The link is provided here. It's easy to find on our main website. Prior to adopting Phoenix, Gilead had been using Excel macros to calculate PK parameters. However, these had the following issues. The macros could produce different results depending on which analyst ran the macro. They were also prone to user error, as well as portability between different versions of Excel. And there was extensive time spent copying and pasting intermediate results from Excel worksheets. The preclinical group was responsible for analyzing PK profiles of large numbers of compounds rapidly to determine which compounds were selected to enter phase 1 first-in-man clinical studies. So Gilead hired our deployment services team to help develop Phoenix workflow templates for their most frequently used study types. And a key finding of the case study is that the use of Phoenix workflow templates reduced the time to perform routine study analyses by 50%. So examples of the Phoenix workflow template solution are presented here with permission from Gilead. So a bit about Phoenix WinNonlin. Phoenix WinNonlin has long been the industry standard for PK/PD modeling and non-compartmental analysis, also known as NCA, and is used by more than 4,000 researchers and over 2,000 institutions around the world. Phoenix WinNonlin provides an intuitive interface for data management, plotting, NCA, individual compartmental PK modeling, bioequivalence tests, table creation, and other PK/PD work. The work performed can be visualized in a diagram where dependencies between steps are highlighted. The workflow structure organizes steps and makes it easy to look at any analysis step by clicking on it. And Phoenix WinNonlin streamlines critical drug development analyses with reusable templates and high-quality output, enabling more impactful quantitative decision-making. So just a brief overview of the Phoenix interface. When you first open the Phoenix application, this is what you see. It's organized by menus across the top of the application, as well as an object browser to view objects, and then a main viewing window. We'll start by making a new project, and you can easily type the project name. And the project has a structure to it. So the top node is the project name. The data folder will accept any input data files that you bring in to the application. And there are some additional subfolders. For example, code, you can write custom code or models and store them here. Output tables, rules for replacement of limited quantification, other documents such as Word documents or PowerPoint slides associated with the study can be saved here. And all of the work that's performed gets done in this workflow section. Let's just bring in a sample data set. This is done on the import menu. And this happens to be a comma-delimited file, CSV format, with some PK data in it. When you bring the data into the application, there's a worksheet preview screen, and it allows you to do things like say whether or not the worksheet has units or not. So I'm simply going to select Has Units row. And in my preview, I see in bold the column names, which identify the data type contained in the column, and then the units are displayed in parentheses here. And at this point, I can simply select Finish and Open to view the data spreadsheet. So the spreadsheet here has a number of subjects who received different formulations, a tablet or a capsule, and then the PK observations are in these columns here. And you can use this data easily in the application to do plotting or analysis. I'll just do some brief examples here. For example, setting up a XY scatter plot, I'm sending the spreadsheet to plotting XY plot. And then I get forwarded to the main mapping panel. Notice that whatever you have selected in the object browser determines the contents of the main viewing panel. We'll just go ahead and map real quick here, and we will group by subject to show all of the subjects on the same plot, and then use formulation as a lattice row, and then maybe make an axis option to choose a logarithmic plot. Okay, so I can very quickly do exploratory plots in the application. You can also use Phoenix to do non-compartmental analysis. I'll do a real quick demo of this. So I just take the same data spreadsheet and this time send it to the NCA object. We'll make the required mappings in the panel and then enter in some dosing information using an internal worksheet. One of the great features of Phoenix is that if you have all of the same doses administered to every subject, you don't have to enter them every time. You can just simply deselect the sorts and say that there is a 10 milligram dose administered to all subjects. And the dosing units get entered in the bottom panel here. And I'm now ready to run my NCA. Okay. The main execute button is located at the top here. Whenever you want to get Phoenix to produce results, simply click this button, and whatever you have selected in the object browser gets run at that time. And then when you click the run, you get taken to the results tab where you can easily browse the output PK parameters as well as the output plots, in this case the regression of the terminal phase. Okay, so for my first example of the workflows will be a rat IV infusion study. So a bit of study background and study objectives. Time concentration data were collected from 3 rats after IV infusion administration of the study compound. And the objective is to use Phoenix WinNonlin to create the following standard outputs. They include tables, which are the time concentration data, dose information, and PK parameter summary tables, as well as some graphs, which include time concentration plots of the type individual animal spaghetti plots, as well as a mean concentration plot with error bars. So the first type of table is the time concentration table. If we look at some of the features of the table, starting from the left, you see the collection time represented in hours formatted to 2 decimal places. Then at the top, it identifies that this is a rat study IV infusion administration with the animal IDs. And the first 3 columns contain the observed concentrations formatted to 3 significant digits. And the table also has the ability to calculate summary statistics. So the mean and standard deviation are also reported at each time point, as well as for certain time points, the concentration was below limit of quantification, and that's represented by BLQ, and therefore the summary statistics can't be calculated, which is represented by this NC for not calculated. The Phoenix tool used to make the time concentration is the table object. So this tool can construct a table with a desired layout and order of display variables. You can specify numeric precision for different elements of the table in either the number of decimals or significant digits format. It has extensive HTML formatting capabilities, superscripting, subscripting, Greek alphabet for mu for micrograms, for example, the infinity symbol for AUC infinity, and so on. And it allows you to enter headers and footers, as well as optional summary statistics. So at this point, I will go ahead and load an example project. We'll start by looking at the input data here. So the input data, this is collected for this preclinical PK study. It has the study number, compound number, route of administration, dose, group, animal number, PK observations here, animal weight, which can be used to calculate the normalized dose, volume of the infusion dose, concentration, target concentration and formulation concentration, molecular weight of the compound, and infusion duration. So to construct the summary table, this is done in the workflow, which I'm now expanding here. So this is an example of the nicely formatted time concentration table. We see it has the same format that I showed in the slide, both with respect to the layout and also the precision of the numeric data. The second standard output is the dose information table. And this includes the animal ID, the body weight of the animal, route or routes of administration, the target and measured formulation concentration, dose volume, and then the dose represented in mass volume as well as in molar. So in this case, the dose is weight normalized and also represented in the molar concentrations. So from the input data, some tools can be used to construct this dose table. The first of which is the data wizard. The data wizard actually is very flexible, and it allows operations such as data filtering, removing outliers or removing a subset of data that you don't want to analyze. You can use it to rename columns, perform unit assignment and unit conversions on columns. It also supports many column transformations, including custom functions. In this case, the data wizard will be used to perform dose normalization by body weight. And once that result is obtained, the result of the data wizard is then sent to the table object to construct the table. Okay, so here's a view of what the data wizard looks like. Look on the Setup tab and see that a number of steps were performed to prep the data to construct the dose table. They include the calculation of the weight normalized dose, as well as unit specification. And then this is the calculation to convert the mass units to nanomolar units, as well as specify the units for that column. So this created two new columns, normalized dose and normalized dose 2. And then this result worksheet, we can see here that the columns were constructed here. And then this was forwarded on to the dose table in the table object. We see here that in different portions of the table, you can toggle between the different types of formatting that you want, and also do things like construct the layout of the table. Another type of output is the plotting. And so with the plotting, these are individual animal plots, also known as the spaghetti plots, where you see all of the animals overlaid on the same semi-log plot. You can do customization of the X and Y axis units directly on the chart, color code by animal number, or you can remove all color and just simply have a black and white representation as well, and easily toggle between log or linear scales for the concentration y-axis. The Phoenix tool used to make individual animal plots is the plotting tool, specifically the XY scatter plot. This allows you to do concentration time plots on linear or log scale, do custom time range as well as axis label options, group by animal ID to overlay them on one plot, and you have extensive display colors and styles for lines and data points. It also supports trellis and matrix plots. For example, you can separate out plots by route of administration or treatment group. So in the Phoenix application, this is an example of the spaghetti plots. And this just took the input data and shows all of the rats. You can see on the right-hand side the figure legend. This is a semi-log plot of all of the rats, nanomolar concentrations versus time. The next output that's a part of the standard study is a mean concentration plot. So this is the average concentration at each time point, and it also has error bars for desired statistics. You can use standard deviation or standard error, for example, to construct these error bars. The Phoenix tools used to make the mean concentration plot include the descriptive statistics tool. This is used to quickly summarize a data set and calculate statistics such as the mean, standard deviation, standard error, variance, coefficient of variation, etc. You can choose one or several summary variables and also retain the option to include a confidence interval. The results of the descriptive statistics are then forwarded on to the plotting tool, the XY scatter plot, to construct the graph, where the new operation here is using SD or SE to make the error bars at each time point. So let's look in Phoenix and see how that's done. So for the mean plot, we use the time concentration descriptive statistics. It's very easy to calculate these. All the settings were just simply to use summarization, summary variable concentration, and then sort by time point so that the mean concentration was calculated each time point. And then the results are, at each time point, you get the output statistics, mean, standard deviation, standard error, and so on. And then this output spreadsheet is then forwarded on to construct the mean plot. You see here the mean plot has the error bars with a title, mean concentration plus or minus standard deviation on a semi-log scale. It's very easy to work with the plot too. So we see here that we have both the error bars up and down. One can very easily go back into the setup and say, for example, you only want the upper error bars. So I'm moving the lower error bar to none and then rerun the plot. And now it only has the upper error bars. It's very user-friendly and easy to work with to make these plots. And the last output requested for this type of study is a PK parameter summary table. This is for individual animal data. And if we look on starting from the left of the table, the PK parameter of interest is listed, and it's formatted the way in a presentation quality figure with units in parentheses. The first three columns containing data are the rat IV infusion parameters for each animal ID, as well as the mean and the standard deviation for each parameter. So the Phoenix tools used to make the PK parameter table. In this workflow, there's some data prep involved using the data wizard. So this was used to perform the dose normalization by body weight. It's also a standard practice to do the BLQ replacements. And this supports a limit of quantification for concentration data and allows you to set up company-specific status codes. For example, the code might be BLQ for below limit of quantification or NS for no sample. And this can do conditional placements. So the replacement that's performed depends on where in the PK profile the BLQ is reported. For example, before Cmax or after Cmax. And this standardized rule set can be saved and reapplied over and over again to each new study. The PK parameters themselves are calculated using the non-compartmental analysis NCA model. A bit of background about non-compartmental analysis. The NCA model types available in Phoenix are governed by the route of administration, which can be extravascular, which is typically anything that isn't directly administered to the systemic circulation is treated as extravascular. It could be PO, it could be transdermal, sublingual, and anything that isn't directly administered. Also, IV bolus and IV infusion are different model types. And then the second criterion for picking the model is the sample matrix, whether it is blood plasma or urine. The NCA model supports sparse sampling as well as serial sampling and can be used to perform single-dose or steady-state analysis. This example is a IV infusion on plasma, and it's a single-dose administration. The non-compartmental analysis doesn't assume a compartmental PK modeling, nor does it do curve fitting. What it does do is calculate PK parameters with standard equations, and this method is highly dependent on sampling times. The reason being that one of the key parameters, the area under the concentration time curve, uses a trapezoidal method. So it basically draws trapezoids, and the more samples you obtain, the closer the trapezoids will be to the actual shape of the concentration time curve. This next plot illustrates some of the key parameters that one gets from NCA. They start with the maximum concentration Cmax, and then the associated time is the Tmax. When calculating the area, a vertical line is drawn down from each observed data point to draw the trapezoid. The area for that trapezoid is calculated, and then over time throughout the profile, you get a cumulative AUC up to the last observed concentration, C last. In the terminal phase, a log linear regression is performed, and the negative slope of this is referred to in the WinNonlin jargon as lambda z. In literature, you might encounter it as a KEL or a case of E. And then this terminal phase regression line is used to extrapolate beyond C last to calculate the AUC infinity. Okay, so these different combinations of route of administration and sample matrix add up to 6 non-compartmental models provided with Phoenix. In terms of the dosing data can be imported from a spreadsheet into Phoenix NCA object and be profiled by different sort variables such as subject and treatment group. Alternatively, you can also enter dosing data manually using an internal worksheet just by typing the value in. The dose units are specified, usually as amounts which can be weight normalized. Some additional options in non-compartmental analysis include the ability to select the terminal elimination phase using the mouse, or use WinNonlin's best fit algorithm to select the terminal phase. You can specify the AUC calculation and interpolation method, whether it's linear or log, compute partial areas under the curve, and set preferred output units and parameter names. That's a bit of the background about the NCA that's used to calculate these PK parameters. In this example, we'll choose a plasma IV infusion dose input with the linear log trapezoidal AUC calculation method and WinNonlin's default terminal phase regression. Once the NCA is performed, you can do optional post-processing with the data wizard. For example, selecting only PK parameters of interest and filtering out those that are not of interest, as well as reduce units or display the unit with the parameter name for presentation purposes. Okay, so we see here, for example, in the pre-processing, the status codes, the BLQ replacements, are set up using these rule sets. In this example, the BLQs, there's a variety of different codes that can be represented here. And then in this section, the conditional substitutions are specified. And the rule set in this case is before Tmax, the BLQ is replaced with 0, and then after Tmax, it's replaced with missing. It also supports the ability to use the static limit of quantification. So in this case, the sensitivity limit for the assay is 2 concentration units. And the optional checkbox here, use when less than LLOQ, is in addition to when the code is encountered in the data set, if a numeric value less than 2 were encountered in the data set, it would also perform the substitution. Here's a look at the non-compartmental analysis model. You see here that this is where you can do the data partitioning for the analysis. And then the dosing is read in from the normalized dose spreadsheet that was constructed earlier and demonstrated earlier in the example. And once the NCA analysis is run, all of the PK parameters are summarized on this table here. The post-processing, this is an example of the data wizard. So the NCA results were then sent on to this data wizard to prepare the data for the table. And there were only 2 steps performed here, one of which was to include only key PK parameters of interest, which are the AUC infinity, half-life, Cmax, mean residence time, volume of distribution, and clearance. And then there was another column constructed for the PK parameter display to ensure that it had the name as well as the unit in parentheses. And so the result from this data wizard was then sent on to the summary table here, the IV PK parameter table. I'll just show you some of the options here briefly. So if you want to, for example, format the column titles, the appearance of these. In this case, the original column was named animal number, and then in the display of the table, this is converted to rat. The statistics column has a nice user-friendly checklist where you can decide which summary statistics are of interest. This is the mean and the standard deviation. And you can also, in the precision alignment, choose that, in this case, it's 3 significant digits for the PK parameters. Okay, so this was an example of the IV infusion study. Next, I'd like to cover the concepts of workflows and templates. So a workflow is the series of data processing and analysis steps used to achieve a particular endpoint, for example, tables and graphs. And we just saw an example of a workflow. A sub-workflow is a smaller workflow used to organize related analysis steps. These are optional, but they are strongly recommended. A sub-workflow breaks down the larger workflow into major and minor steps. And this simplifies troubleshooting if an error were to occur in the workflow to a particular sub-step. So we see in the chart example here, one of the sub-workflows is number 3, prepare data for NCA dose input and dose table. So everything related to constructing the normalized dose is organized in that sub-workflow. They're very useful for data prep or post-processing. And then the last sub-workflow, number 10, is where all of the output tables and plots are stored. So one could easily just load the project and go to sub-workflow number 10 just to see all of the outputs of interest. Next concept is workflow templates. Depending on the study type, a workflow may require many data prep, analysis, and post-processing steps to set up the desired output tables and graphs. Wouldn't it be nice to automate these repetitive setup steps while still ensuring the accuracy of the results and the uniformity of the tables and graphs from study to study? And the solution presented here is the workflow template. In order to enable a workflow template, the first step is to construct a data link. And what is a data link? Data links are powerful tools with the following properties. They can accept external input data for a given study type. When I say external input data, referring to a file such as an Excel file, CSV file, or SAS transport file that contains the PK observations. The data link also knows the order in which each object appears in the workflow, and it also knows when and where to forward input data to each analysis tool in the entire workflow. Why use a data link? Why is this important? Well, in this example, if we look at the bottom presentation first, if there are many different analysis tools in your workflow, without a data link, you would need to manually map data to each and every one of these individual tools, which is very time-consuming and repetitive. The data link is a placeholder for new data, and it knows to forward this new data on to different parts of the workflow in the order of operations that were performed. So summary steps to create a workflow template. So first, create the workflow of interest to produce all desired outputs. Next, set up a data link for external input data. And then export the workflow as a template file. This file has the extension WNLT and can be used over and over again with new data for the same study type. The workflow template remembers all the settings associated with every object in the workflow. All of the data mappings, fonts and styles of plots and tables, layouts, and so on. Once a workflow template is created, to reuse it, do the following steps. Create a new project in Phoenix, import the data from the Excel or other external file type, then import the workflow template for the study type of interest, connect the imported data to the data link, and then execute the workflow. And this series of steps will be demonstrated in the next example. Next example is an IVPO study conducted in dogs. Go ahead and close my previous project. So I'm going through the steps here of importing data and a workflow template for an IVPO study. First, I'll go ahead and import the data set. So this is an Excel file that has two worksheets. So I simply browse, use the double right arrow to look at each spreadsheet. In this case, spreadsheet number 2 has a units row, so I'll check that and then click Finish and Open. Okay, so in this spreadsheet, we see the PK study number, compound number, and then the route of administration. In examining the data set, we see that some of the dogs received the infusion and others received the extravascular administration. Okay, and then the dose amount is listed here, animal number, PK observations, other information used to calculate the normalized as well as mass volume and molar doses, infusion duration, species, and plasma matrix. For this example, the study background and objectives. So time concentration data were collected from dogs after IV infusion or PO administration of the study compound. The objectives are to use Phoenix WinNonlin to create the following standard outputs. The tables of interest include a time concentration data separated by route of administration, the dose summary table, PK parameter summary table separated by route of administration, and then a combined PK parameter summary including the bioavailability calculation to get fraction bioavailable. The graphs include the individual animal spaghetti plots, as well as a mean concentration plot with error bars. And so to perform all of the steps required to produce these outputs, a standard IVPO workflow template was created. And I'll show how to use that with this data at this time. I'm going to the File menu and select Import. And this time, I'm selecting the WNLT file, General IVPO Workflow, and go ahead and bring it into Phoenix. Okay, so we see here, this is the workflow. It's organized into a nice flow diagram with all of the numbered steps. The first item here is the data link, which is ready to accept concentration data and then forward it on to all of these different steps in the workflow. And the only steps I need to do here to make this work are to go to the data link and bring in the input data, run the data link, and then go up to the workflow. And at this point, I've selected the workflow, and Phoenix will run the entire workflow. You can actually see in the bottom status panel there what step is being performed as Phoenix produces all of these outputs. Okay, and we see that it only took a few minutes to create all of these output plots and graphs by running the workflow. So in this example, some of these are similar operations that were done in the previous IV infusion study. The time concentration tables, dose tables, individual animal plots, and mean concentration plots can be constructed using the same methods shown in example 1. So I will briefly just look at some of these outputs here. So the time concentration for IV data, the time concentration for PO data, and notice that the different dogs got different routes of administration. And how was this possible to split these into different table types? We'll look at this the sub-workflow here, which uses the split worksheet object to split the extravascular and infusion concentrations. And it's just a very easy step of simply sorting by route and running the split object. It creates one sheet for only the extravascular administration and a separate sheet for the IV infusion administration. And then you can forward these on to create these individual time concentration tables. Okay. And this is also used to allow you to plot the IV and PO separated. So in this case, we have an example of the spaghetti plots. And this is a semi-log plot of the dog data. Notice by the title that this is the extravascular administration. And then page 2 shows the IV infusion administration. Okay, and then the descriptive statistics, this is used to make the average concentrations at each time point. And we notice here that this is the route column is included in this calculation, which then allows you to do a different mean plot for IV and PO data. So the descriptive stats are then sent on to the split worksheet to split the extravascular and infusion data. And then these are forwarded to the IV plot. So we have here this overlay plot that shows the mean IV and PO concentrations plus or minus standard deviation, and then the legend shows whether it's the infusion or the extravascular. Okay, next I'll cover some of the new operations that are different in this workflow template. In the non-compartmental analysis, in the dosing setup, you can use the dosing defined option to simultaneously model IV and PO concentration data. And many of the other selections then are similar. It's all plasma data. You can map time and concentration variables and specify the AUC calculation method. Then for the post-processing, you can split the worksheet and use the data wizard to split IV and PO output parameters into separate worksheets, as well as reduce units or display the unit with the parameter name. So the requested output, next output for this type of study is the PK parameter table, and there's a separate table for the infusion data as well as the PO data. And these are the summary of the output parameters with summary statistics for each individual dog in this case. You can use the table object as before to construct these tables. In this case, the BQL rules are applied as described previously with the same rule set. And just highlighting what's new in this example, this is the non-compartmental analysis. And we see in the bottom panel here this dosing defined section. So what that allows you to do is you can go to the dosing setup, and then the dose type selection is governed by the route of administration. And so both the IV and PO data can be run in the same NCA model object. Let's have a look at the results. So if you examine the plots, this is the terminal phase regression for each animal. And then in the final parameters sheet, you see all of the PK parameters calculated for each animal. Okay, and to prepare the PK parameter tables, the split worksheet is again used to split by route of administration. And then you get the different PK parameter tables. So the IV split was sent on to the IV PK parameter table. See the nicely formatted PK parameter summary for each dog that received the IV infusion administration. And then the second table is the extravascular PK parameter summary for each dog. And then a further step is in this sub-workflow allows the bioavailability calculation. So in order to perform this calculation, you can use a variety of data tools. They include the merge tool to combine two worksheets with the same type of data, split worksheet, join worksheet, add data from one worksheet to another for further manipulations. Stack allows you to vertically join two worksheets. Append, you can add specific pieces of one worksheet to another, or pivot to shift the data axis display. So how is this bioavailability calculation performed? Well, the tools used are the split and join worksheets to combine IV and PO PK parameter results from NCA, and then use a custom function in the data wizard to calculate F using the equation presented below. Once this calculation is performed, one can send it on to the standard table object that was covered previously. So if we look at this calculate bioavailability sub-workflow, you see that we've joined the IV AUC mean and dose into a worksheet, and then the data wizard is used to calculate F. So this is basically just putting the IV and PO AUCs and doses together into one worksheet, and then using a column transformation custom function to calculate F. And the formula is actually applied in step 2 here. So this is the custom formula. Then on the results tab, we see this the parameter F, and then the PK parameter displays F with units and parens. These are then forwarded on to construct the combined PK summary table. In this table, we see the route of administration, animal ID, parameter of interest, including F. It's actually the third from the bottom in the PK parameter list, associated units, mean, and standard deviation, and so on. So a few words of advice for generating these workflow templates, getting to know the Phoenix tools and use sample data sets, Start with the most common and all-inclusive study design as the foundation for building additional workflows. And know what you want from the data outputs. And then that governs the choice of which type of tool is used to construct the workflow template. We also recommend labeling each step in the workflow with numbers and specific titles, so it's very easy to backtrace and find any step that you want to modify. And then collect feedback from analysts to make sure the template is robust for any data set. So this concludes the formal presentation. At this point, my colleague Suzanne Minton, our marketing specialist, is available to help with the questions that have come in, and we'll go ahead and address those at this time.
Hey everybody, first question. How can I get Phoenix results into Word or Excel?
Okay. Thanks, Suzanne. It's very straightforward to do this. To get outputs into Word or Excel, you can export. So let's look at an example here where we have NCA model results. To get any Phoenix worksheet into Excel, you can simply select the spreadsheet of interest, right-click it, and then select Export, and then choose the Excel format. In this case, it's the final parameters pivoted as an Excel file. Okay, and we see here now this is, I'm opening the file in Excel, and voila, very easy to put it into Excel. You can also export tables to Word. Let's take this, this combined PK summary. The table is in HTML format, so a recommended first step with this table type is to right-click and select Copy to Tables folder. And then to export anything in Phoenix to Word, use the File menu and then select Word Export. And let's just basically take the output of interest, which is the PK summary table, and then click Export. Okay, and you'll get this prompt here that lets you know that export is successfully completed. And then on your taskbar, you'll see the Word icon appear, and then your nicely formatted table is put out into Word. Next question, please.
Can I set a standard save location for Phoenix projects?
Sure. So when you're doing work, especially lots of different studies, in order to help with file management, it's easy to set a standard location. And that can be done under the Phoenix Edit Preferences menu. Then under the General tab, select Projects. And in this case, I've set the save location to this directory on my machine. So whenever I select File, Save Project, or File, Save Project As, it knows to go directly to this, this directory. So I'll just go ahead and save this project from Webinar and click Save.
Okay, and it looks like we have one final question. Can I use other software such as SAS and non-mem with Phoenix?
Yes, it's certainly possible to use SAS and non-mem with Phoenix. That can be done if you have a Phoenix Connect license. So what I did was select Help About Phoenix, and we'll see in the active licenses here that this allows WinNonlin 6.3 as well as Connect 1.3. And in Phoenix Connect, there are a series of shells. There's a SAS shell, non-mem shell, that allows you to call up SAS or non-mem, run it, produce results, and then return those results into your Phoenix project, and then you can connect it to any of these other data tools that I've shown in the webinar here. Okay, if there aren't any other questions, I do have one additional example to display. So I'll go ahead and move on to show that. Okay, so I'll show one more example. This is a rat bile study. And this is a brief example of a workflow template, and the study background is that bile concentration data were collected from 3 rats after IV infusion administration of the study compound. Then we'll create the following standard outputs. Time concentration data sheet, the cumulative % of total dose recovered, PK parameter summary table, and then a mean cumulative % of total dose excreted in bile. So the time concentration tables can be constructed easily using the same methods shown in example 1. What's new about this example? Well, in this example, bile collects in the gallbladder over a period of a few hours, and then the entire bile is collected. The concentration is measured as the midpoint of this time interval. So rather than getting a discrete measurement directly from blood plasma, what happens is the midpoint of that collection interval can be used to perform non-compartmental analysis. And the model type that supports this in Phoenix is the urine model, designed to analyze data collected over a time interval. So it's a similar method. In the urine case, you're just collecting urine from the bladder over an interval instead of the bile. Highlight some key parameter differences with the urine models. For example, max rate instead of Cmax, amount recovered, and % recovered. And then use the data tools to calculate % recovered with respect to the total dose. Okay, so I'll just very briefly demonstrate this. And we'll bring in bile data set. So this is an example of another study type, which would get its own workflow template. Okay, and we'll go ahead and run the workflow for the bile study and discuss some of the unique features of this workflow template. Okay, so the workflow template has been run. And I'll focus a bit on the NCA model. So if we look in this bottom section, this is the urine type of model. And there's some different types of required inputs. Looking up at the mapping panel, the orange columns are the required inputs. So there's a start and end time for the collection interval, a concentration and volume of the sample. And in the results, we see the parameters listed as max rate instead of Cmax. You also get an amount recovered as well as a % recovered. And then these NCA results are used in a similar fashion as before to construct some specialized tables here. So the cumulative % of total dose recovered. So this is total dose excreted in bile in %. And then notice in the time column you see the interval instead of a discrete time point, the animal ID, and then the %. The mean cumulative percentage of dose excreted is plotted on this graph type. And then the PK summary for the informatics group is listed here, where we had some standardized unit presentations done and you get the amount recovered and the mean and the standard deviation for each output parameter of interest.
Chris, I think we have one final question. Can you show the audience how to join and split data?
Join and split data, sure. So let's go back to the PO template. I'm picking this one because it has two different routes of administration that allow you to do the splitting and the joining. Okay, so this is the main spreadsheet where we have route of administration here. And if I want to split these into two separate worksheets, it's very simple to do. All I have to do is send this to the data group and then choose split worksheet. And I'm going to put this in this general workflow here so it's easy to see it compared to everything else that's in here. And then simply sort by the route of administration, and then run it. And so what you get are a row count, so there's 30 rows of extravascular data, 30 of infusion, and then all of the rows associated with extravascular get put into one output sheet and the infusion in a separate output sheet. Okay, and then to join worksheets, the join operation is asking for two different worksheets. So in this case, we've got two worksheets. One is the mean normalized IV dose, and then the other is to the IV AUC mean parameter result. So when you do a join worksheet, you basically map two different worksheets together, and then you need a key variable that's the same between the two worksheets, which in this case is the route. So the route is then used as a sort variable for the join. And then in worksheet 2, we see that again, you choose the same variable to join. Okay. So what happened is we have one worksheet here that includes the source data, and then the second bit was from the descriptive stats. So you get the original, you get the mean from one worksheet, and then the descriptive stats from a second worksheet. And you notice here that these outputs have turned pink. That's just to let you know that a previous step was executed. It's very easy to just re-execute everything and refresh your analysis. This is an append step. We'll execute this sub-workflow next. And then only the plots that were affected by that join step are out of date. So I can just simply rerun to refresh the analysis. Okay, so we're coming up at the end time here. Thank you all for your attention and joining today and for your questions. I'd like to wrap up with the contact information. So if you're interested in learning more about Phoenix or getting Phoenix, depending on where you are, the best contact information is listed right here. This concludes the WebEx. Thanks once again.